All right, guys, we're going to review exploring bivariate data in this lesson. So graphing bivariate data essentially is just trying to graph a scatter plot. So scatter plots are a graph showing the value in a response variable given the value of an explanatory variable. And so what we always need to understand is that the explanatory variable is going to be graphed on the x-axis, whereas the response variable is going to be graphed on the y-axis when we're concerning scatter plots. There's also such a thing as association when we're looking at scatter plots. So the direction of the value of the response variable as the explanatory variable increases. So, if you have a scatter plot that looks like it's trending upwards, that's going to have a positive association. One that trends downward is going to have a negative association, whereas if you have, data kind of all over the place, or it's going in a straight line across, that's going to have no association in this case. We also have strength when we're talking about scatter plots. So that's how well the plotted points fit to a linear pattern. So if the plotted points are very, very much in line, either positively or negatively, that means that R is going to be either very close to 1 or very close to -1, or right at 1 or right at -1. If the data, strays away a little from a linear pattern, it's still kind of all over the place, but you could draw a line right through that data. If it's going in a positive direction, that means R is going to be close to +1, or if it's going downward, R is going to be very close to -1. Then if the data does not have any sort of pattern whatsoever, so the further away from a pattern the data actually gets when we're looking at a scatter plot, that means that it's going to go closer to 0 in that case. Okay. We also have this idea of a correlation coefficient. So correlation is essentially how well the plotted points fit to the line. This is also known as the correlation coefficient, and this is the calculation of strength, essentially. So this determines, or this R value essentially determines how strong the data is in a linear pattern. Correlation, however, does not imply causation. So it's important to note that when we're looking at examples, no matter how strong this is, that doesn't mean that the response variable explains the explanatory variable or caused the explanatory variable, or vice versa. It's not going to prove causation in this case. We also have a coefficient of determination, which is essentially the same thing as a correlation coefficient, and that's the percent of variance in the response variable as explained by the change in the explanatory variable. And this value is noted as R squared. We also have a least squares regression line, and that's the line that minimizes the sum of the squares of the residuals of a set of bivariate data. And so essentially what we need to understand is that this line represents the residuals, and that's the difference between a predicted value using a least squares regression line and an observed value. That's what residuals are basically. So when we look at this example right here, an insurance company conducts a survey of 15 of its life insurance agents. The average number of minutes spent with each potential customer and the number of policies sold in a week are noted for each agent, letting X and Y represent the average number of minutes and the number of sales respectively. We have this data right here. So X represents the total number of minutes that each insurance agent spent with a customer or customers, and Y represents the total number of sales based off of how many minutes were spent with that customer. So let's say that we're asked to construct a scatter plot and describe the relationship. So if we input all of this data into stat edit and then construct a scatter plot, we'll note that it has a positive association that's fairly strong. Okay, so there's a strong positive linear relationship between the number of minutes spent per customer by an agent and the number of policies sold in a week. That makes the most sense, in all honesty. From there, if we wanted to calculate the correlation coefficient and show our work, showing our work and explain in context, we do not have to find all of this by hand. We don't have to do all of that math by hand. What we can do is we can actually go over to stat. So again, this is to input the data, stat, edit, and then this is to find R and R squared. So this would be stat, calc, and then 8. Okay? If we did want to know, however, our x prime and y prime and the standard deviation of x and the standard deviation of y, which is essentially representing either the mean and standard deviation of x or the mean and standard deviation of y in this case, we would need to go to, so to find this information, we would need to go to stat, calc, and 2. And then find our 2 variable statistics based off of the data that we have entered in up here in stat edit. But that's going to give us our mean and standard deviation for both of those. But once we enter in stat calc and 8 for the linear regression, that's going to give us an R value of 0.8836 and an R squared value of 0.7808. So our correlation coefficient is 0.781, therefore approximately 78% of the variation in the number of policies sold can be explained by the number of minutes spent per customer. That is how we will interpret our correlation coefficient or explain in context. If we're asked to calculate a least squares regression line based off of that, again, you should be able to note that A up here represents your y-intercept and B is going to represent your slope. So again, you can use stat calc 8 if you need to in order to determine what the least squares regression line is, or if you needed to, you could take whatever the R value was times the standard deviation of y divided by the standard deviation of x, and that's going to give you 0.5492. If we're asked to interpret that slope in context, with each additional minutes the agent spends, they sell approximately 0.54 additional policies. So that's what the slope represents in context, and you will probably be asked something similar to that. If we're asked to find the y-intercept of that, that's going to be represented again. The y-intercept is this A value right here. So again, go to stat calc 8, you should be fine. But the y-intercept is going to be represented by whatever the mean value of y was minus the slope, or B1, times the x, the mean of the x values. And that's going to give us a value of negative 1.73. And if we're asked to interpret the slope, or the intercept in words, when the agent spends 0 minutes per customer, they can expect to sell negative 1.73 policies. Okay, let's say that we're asked a question to make a prediction for the number of policies sold by an agent who spends 24 minutes per customer. Well, we know that our line essentially is going to be y hat is equal to negative 1.73 plus 0.5492x. All we need to do if we're asked this question is plug in 24 for x and then solve, and that's going to give us an approximate value. So if we're asked to make a prediction in this case, the agent can probably sell about 11.45 policies if they spend on average 24 minutes per customer in this case. If we're asked to, if we're given a residual plot with values, we want to use these values and the residual plot to answer the questions below. So here's our residual plot, which again represents the distance away that each data point is from the least squares regression line. And then these are the actual residuals themselves, what's represented in L3 right here. So basically what this means is that if we took each one of the values in L1 and plugged them in to our least squares regression line, which again is represented by this, if we plugged all of those in for x and solved, then this is what we would get for our residuals right here. So if we're asked the question, is a linear model appropriate for the relationship between minutes and policies sold? Yes, the residual plot shows no pattern, so a linear relationship is appropriate. And we could tell that from the scatter plot as it was. Second, if we're asked to calculate the standard deviation of the residuals and explain in context, what we can do is we can, again, just find one variable statistics right here. So go to stat, calc, and 1, and then plug in L3 for that, and that's going to give us our standard deviation for that. And so that would give us a standard deviation of 1.31 for those residuals. So the typical difference in actual number of policies is sold from the predicted amount varies by about 1.31 policies. That's how we explain that in context. We also have outliers and influential points. So an influential point is just a point whose removal would sharply change the values of the regression line, and outliers are essentially kind of the same thing, a point that falls far outside the linear pattern of the other observations. So in this example right here, if we're looking at this, a scatter plot of grade point average versus weekly television time for a group of high school seniors is as follows. And you'll notice that the less time they spend watching television, the higher their GPA is, whereas it tends to taper down the more weekly hours of television they watch. So by direct observation of the scatter plot, we note that there are two outliers. One person who watches 5 hours of television a week has only a 1.5 GPA, and another person who watches 25 hours weekly yet has a 3.0 GPA. Note also that while the value of 30 weekly hours of television may be considered an outlier for the television hours variable, and 0.5 GPA may be considered an outlier for the GPA variable, the point 0.5 is not an outlier in the regression context because it does not fall off the straight line pattern. So what that means is that this point is not considered an outlier. However, these 2 points right here could be considered outliers or influential points in this case.